a bunch of problems. And once again, I feel like this is the time when it's just going to take, because you have to kind of work at these things a little bit before you're really receptive to, to learn it. So what I am going to do, I do want to have, I don't know if we'll do it this time or next chapter, but we're going to get to a point where I am going to ask you to do a test where you're going to have at least part of it here soon. That's not going to be on the computer, right? I am going to want to see your work, and I hate kind of doing that in a way because I like doing that, but it does limit me a little bit. So, but I think we're about ready for that. And so I want you, because the process is becoming very important. As we move into the next chapter, the process becomes even more important. But what I want you to do here is I want you to maybe take some notes. So get out your notebooks, and I would like you to kind of, I rarely ask people to write stuff down, but I'm going to do this slowly enough, and slow me down if necessary, so you can actually go through the process with me and do it properly. Right? Do the work the way, organize your thinking and show the work the way you should for a physics problem like this. All right, so some of these are pretty quick. First one's really pretty quick. You've got your updated formula sheet. What do we want here? What's the equation that's useful? Period of pendulum, yes. So period of pendulum, we know that T equals 2 pi times the square root of L, which is what? Length, divided by G, which is what? No. It's the acceleration of gravity of the surface of the Earth, right? So we're doing pendulum physics on the surface of the Earth, or near it. And what are we trying to do here? There's a couple ways we can go about this one, so let's talk about this. Let's do this maybe first the most straightforward way, and then see if we can come up with a slicker way of doing this that doesn't require as much writing. So we know they give us a pendulum length of 4.70 meters, so let's write down the values of our variables. What is that? What variable? Length. So we know L equals 4.70 standard units, right? We want to know what would the length need to be changed to in order to double the pendulum's period, right? So let's call this L sub 0, or L naught. That's our initial length. And we're trying to find the new length, right? So we'll call it L. Well, what would I do? Good, so one thing I probably want to do is solve for the initial period, right? So all we'd have to do is plug this stuff in, right? If I want to solve for, let's call it T naught, our initial period, it's just going to equal 2 pi times the square root of 4.70 over what? 9.80. Okay. And that's going to give me some calculator number. In fact, let's pull up the calculator and get that calculator number. All right, so we'll go 2 pi times square root of, I didn't really need the times, did I? 4.7 divided by 9.80. Okay, and voila, I get some number. Okay, so it's roughly equal to, we're going to keep our calculator number in the calculator though, right? It's roughly equal to 4.35. What would the units be of that? If it's the period of a pendulum, what's that measuring?
Time.
It'd be time, so it'd be seconds. That's how long it takes to swing through one complete cycle, right? So then, if we want to figure out the length of, we're trying to solve for L, what could I do?
So just multiply that by 2.
Okay, good. So then, this is T naught, right? So T must equal 2 times that number, which is stored in my calculator. Agreed? Okay, so then all we got to do is take this equation up here. take this equation and we're gonna solve this thing for L, right? So if I wanna solve this for L, what do I have to do to that equation? What are the steps? Reverse order of operations, good. So what's the first thing I would do if I wanna get this L by itself? What's the first thing I would do? Divide each side by 2 pi. So that's gonna give me, let's flip it around too, so I get the square root of L over G equals, on this side I would have had 2 over 2 pi. Now what? Square both sides to get rid of the square root, right? And then what? Times by G, right? And so I get L equals G times that. Right? Does that make sense? And those are all numbers. I can just plug that in on a calculator, right? Okay, we found.
Would it be squared?
Say it again.
Squared.
Oh, squared. And this was T naught, so T is just 2 times that, right? Okay. So let's multiply that one times 2. So there's T, right? That's my new doubled period. So now let's just evaluate this expression. So we're going to get, our answer is going to be G 9.80 times the quantity. I'm even going to put in, let's even use our fraction template here, get real fancy. The quantity T, which is that number, right? Divided by.
Why does it say 7?
That's really weird. Why does it say?
0.7. Forgot the 8. Forgot the 8. Just delete it and put answer.
Oh, wow. That's really, why did it do that?
You need to keep it very calculator.
Never seen anything so crazy.
Well, just delete it and put answer. Just 2 seconds. That's so weird. Delete.
Okay, I could put answer. I should be able to just go up and grab that number, though. That's really strange. There it is. Why did
That
it-
is so weird. Just roll the calculator at the bar.
Yeah.
Do you know how to grab the number and put them on the bottom?
Oh, yeah, I know how to do that. So if you, so go hit down, and then second up.
Second up. What do you mean?
Yep, second and then up.
It just turns the brightness up.
Or alpha up, sorry, alpha.
It's blinding us.
He's like, wow, that's right. Alpha up, alpha up.
Alpha.
Alpha
up.
and then it goes straight up, and then you hit enter, and then it'll.
Oh.
I didn't know that. Yeah.
Oh, that's pretty cool.
Yeah,
Huh.
I just taught you something, just go ahead.
You did. You did.
Don't like that.
I like that. I like that. Okay, so then on the bottom we just wanted 2 pi, right?
Yeah.
So 2 pi. I'm gonna close the quantity, and I'm gonna square it. And that should be my answer, shouldn't it? Right? Everybody agree?
Yeah.
Okay.
Yes.
So the answer is 18.8. Questions?
Do we want to check that?
Sure.
Yeah.
Okay.
Mode, check.
So if we go, I don't know if I've got this. I don't know if I can. I kind of don't think I can. I don't think I've got that assignment, but that's right. That's right. Okay, there's another way to do this though. That's great. That worked. No problem there. But let's look at this original equation here, and I want to see if you could maybe think of another way of doing this. Okay, if I'm going to double the pendulum's period, now look at this equation on here, right? This is how T and L are related, right? T is proportional to the square root of L, right? So if everything else is staying the same,
Why don't we just change that 2 to 4?
so yeah, what would have to happen to this? if we want to double t, then what would I have to do to the L if it's proportional to the square root of L?
Just half L.
You see how that works? You see what I'm saying? If I were to double L, for example, what would that do to t? It's not going to double t. It's going to, because if I multiply L by 2, that's inside the radical, right? And so I would really only be changing t by the square root of 2. You see what I'm saying? Right?
Should be 4L.
So yeah, right? You see how that is? That t is changing because the L is being squared. T is changing as the square of whatever's happening to L, because L is inside the radical, right? So if I'm doubling the period, then that actually means that that's going to correspond to a quadrupling the length because it's inside the radical. Does everybody see that? You don't have to do it that way, but I'm saying that could save you a lot of hassle, couldn't it? Because then all I've got to do is say 4.70 times 4 is what? Well, that's our answer. 18 point, what do we get? 18.8.
Exponential relationship. So like
It is.
If it was,
Yeah, it
if
is.
it was being tripled, it wouldn't just be.
It'd have to be 9.
Yeah.
It'd have to be
Yeah.
9, not 6.
Right, so if we're saying that t is proportional to the square root of L, what if I squared both sides? Then I'd get t squared is proportional to L,
Well, that
right?
makes sense times 8 by 4 though, because that's like double on each side.
Yeah, it is, right? So if I'm doubling t, then I would be saying like 2t squared, right, is what? Well, that's 4t squared is proportional to L, right? See what I'm saying?
Yeah.
So it's actually increasing by 4 times what the original value was. You see how that works? Okay. Right? Doubling here is actually increasing by 2 squared on this side. Okay. If you see that relationship, you would have just known. Take my original pendulum length times 4. You can do it the long way, but that's just a lot quicker by seeing the relationship between everything else is staying the same. So you can just isolate the relationship between those two variables, right? T goes as the square root of L, so L goes as t squared. Okay?
Wait, so you would times T by 4 or L by?
You would multiply, so if L goes as t squared, right? If I'm doubling t, then that means that 2 squared is 4. I'm actually increasing L by a factor of 4, right?
So if you were to write the equation as if you were going to do that way, you would do 4t squared equals 2 pi square root of L.
Well, okay, so if we were, yeah, I mean, but we don't even have to, all this stuff, here's another way of looking at this. All this stuff right here is constant, right? Everybody see that? So an easier way of writing this would just be to say that, see if you like this better. Easier way of saying that would just be t equals some constant times the square root of L, right? So if I'm going to double t, if I square both sides, right, to get the L by itself, if I square both sides, I get t squared equals k squared times L, right? K squared, let's just call that constant c. It's still just a constant, right? So that's not going to change. So if I'm doubling t, look what we get. 2t squared, right, is going to give me what? Well, that's going to equal 4t squared. That's going to equal c times whatever my new, call that my initial length. That's my new length, right? Well, what is that? That's 4 times t squared. T squared was c times my original length, wasn't it? Right? So it's 4 times what I started with. Right? Make sense? Okay, and so
If it asked you to triple it, would you multiply by 6?
if it asks you triple it, you'd multiply by 3 squared, so it'd be 9.
Yeah,
9 times longer.
and then 4 would be 6 too.
Yep. You don't have to see that. It's not like that's essential. The way we did it the first time is fine. It works, but that's just a little more elegant way of looking at it, I think. All right. I am recording this. Yes. Okay, next. How about this guy? I like this problem. Maximum force on that a grocery sack can withstand and not rip is 237 newtons. The maximum acceleration the sack can withstand when 20.9 kilograms are lifted from the floor is what? So what's the maximum acceleration that sack could experience before it rips, right? So here's where we do need a free body diagram this time. We do. So what are the forces acting on the sack? Because the sack is going to be the object that we're worried about. Okay, good. So we're going to have the upward force, which is the lifting force, I guess. Call it L for lifting force. And then what's the downward force? Okay, good. So that's just going to be mg, right? Mass of whatever's the materials in the, what the sack weighs when it's full, times acceleration of gravity. Okay. And by Newton's, those are the only two forces acting, correct? So by Newton's second law, then, we know that the net force is going to be the sum of those forces. Which one's positive? Yeah, up is positive, right? Vertically. So we get positive L minus mg. And what is the net force equal to? Mass times acceleration, right? Okay. And really, we're just solving for acceleration, right? Okay, what is the maximum lifting force that we could apply? 237. Anything above that and the sack is going to rip, right? So we know what that is.
What does L stand for?
Lifting force. Okay. We know the mass of the loaded sack is 20.9 kilograms. So that goes there. And G is a constant, right? So what do we do? Just divide both sides by M, right? And we get A equals L minus mg over M, and I just plug in numbers.
But I'm confused on the mg part.
Okay. What's the... Go ahead. What about that?
Because, like, how do you solve for A because you don't know mg?
You actually do. Mg is just the weight of the sack, right? Does that make sense? When I'm holding this sack, so here's when I'm holding this sack at rest, what are the only forces acting?
Gravity.
Okay, so gravity, the weight of this thing, I've got something in there, right? So that's the weight pushing down, and then my lifting force pushing up, right? Now, if I accelerate this thing upward, does it change the weight inside the sack? No, it doesn't. That's still the same weight pushing down. But now I've increased the lifting force, and so it's going to accelerate. Now there is going to be a net force. When it's at rest here, there's no net force. I'm lifting with exactly the same force as the gravity's pushing down on the magnet, right?
Yeah.
But if I accelerate it now, that means this force is going to become slightly larger, which is going to give us some net force upward. If I add these two things up vectorially, what I should see is this. I should see that there's going to be some net force upwards, because it is accelerating upwards. But if I lift too hard, I'm going to rip the bag. It can only withstand so much lifting force before the bag's going to rip, right? But I want to pick it up as fast as I can. So I want to see what's the maximum acceleration I can impart to this bag without ripping it. Yeah.
So mg, did that stand for mass and gravity, or just?
Yeah, mg is just mg always just means mass times acceleration of gravity. That's always weight, isn't it? Right. The weight of any object is just its mass times the acceleration of gravity.
So to solve for it, you would type in the 237 minus the 20.9 times 9.8.
Exactly. So if we,
Divided by 20.
so we're gonna get positive 237 minus 20.9 times 9.80 divided by 20.9. And then whatever number we get back is gonna be the acceleration, maximum acceleration. Right? Make sense? What would happen? Okay, so let's what's our answer? I want to show you something kind of cool here. I just thought of something that might teach you some good physics. So if we plug this stuff in, we get the quantity 237 minus 20.9 times 9.8, I don't need the zero, right, divided by 20.9. So that's my answer, 1.54, 3 sig figs, yeah, 1.54 meters per second squared. Okay, let me show you something cool. Let's pretend, I'm gonna let x be, I'm gonna write that same expression out, but I'm gonna let x be the mass of the loaded grocery sack, okay? So then I would get the quantity 237 minus 9.8x divided by x, right? Everybody agree? Okay. Well, I'm going to set the value of x. If I set the value of x at 20.9, so I'm going to store that as x. And now if I go up and grab that expression and evaluate it, I'm going to get back what, my 1.54, right?
How did you set the value of x again?
All you do is you just store it. So I type in a number and I store it as x.
I always thought that meant stop for some reason.
No, that's store.
Whoa.
Okay, so now what's really cool about this though is I want you to make a prediction. There's some really good physics going on here. So what do you think is going to happen if I decrease the mass of the sack? How is that going to impact the acceleration? Think about that logically. If this thing's really, what's it going to do? It's going to increase it, isn't it, right? Because if this thing is really heavy, I'm not going to be able to accelerate it very hard before it's going to tear the sack out, right? If it's really light, I could pick it up with a lot of acceleration and it wouldn't tear the sack. Agreed? Well, we can witness that. What if I were to, let's just let the value of x go to 10, for example. See what happens. So if I store 10 as x, and I go back up and evaluate, I grab that expression and hit enter to evaluate it. What'd I do? Oh, I think I must have.
Oh yeah, you did them in the same equation.
Oh, okay, hang on. There.
Store 10 as x times.
Let's roll this down. So I gotta go.
37 minus.
Okay, so there's. Okay, so there's my answer. Now let's go down and go 10, store x. I gotta hit enter. So now I stored it. Then I go up. Well, look at that. My acceleration went up by a lot, didn't it? Maximum acceleration, right? As predicted, right? It works. Okay. How would I figure out what would be the biggest value I could input before x before this became impossible?
3. What do you mean?
What was, in other words, what's the threshold weight?
237 minus 9. Yeah, set the value to 0, acceleration to 0, and then solve for.
Yeah. What's it going to be?
A lot.
What would be the weight of the bag at which I couldn't accelerate it at all? I'd have to just pick it up at constant speed. 237, right? Would be the threshold. And beyond that, I couldn't even pick the bag up. It would rip guaranteed. Right?
Well, if it
I
was
guess technically like 236 points.
Because the
Yeah.
bag rips
At 237.
anything above 237.
But, so it'd have to be 237 times 9.8.
No. Well, if I set the acceleration equal to 0,
Yeah,
I would be just, well, you said the right thing.
set the acceleration to equal
Then
to
I'd get
0,
L
and
minus
solve-
mg equals 0. So mg would have to just equal L, which is 237.
And this is like, is it standard units?
Yeah. right?
Wait, so could you pick it up with that 30 seconds?
I couldn't. If it was at rest, I couldn't accelerate it. But if I happened to get it moving a little bit, I could keep it moving at constant speed. Right? If I pushed on it from the bottom or something to pick it up a little bit, then I could pick it up with constant speed. But if I tried to accelerate it at all, it would rip. Right? That makes, I mean, I'm just kind of. All right. Questions on that? Does that make sense? How about this? Another one I think is pretty good here. So once again, we got to start here with the free body diagram, right? So we've got this sled that's being pulled across flat ground. Okay, we're pulling, and I didn't say this, but we're going to assume that we're pulling horizontally on the sled, right? So then here's the sled, right? Using our boring free body diagrams, it's just a point. What are the forces acting on the sled, and in what direction? Okay, somebody raise your hand. Give me one force. Give me a force. Yes. Friction. Okay, so if the sled is moving to the right, in what direction is friction acting?
Left.
To the left. Okay, good. So we've got friction acting to the left. What's another force? Yes, ma'am.
Tension.
Tension. Good. So we've got the tension force acting to the right. Good. Okay, those are probably the first ones that get mentioned because they're the most obvious, because the sled is moving horizontally. Are there other forces acting? Yeah. Okay, we got the weight of the sled, which is pushing down. And so notice that's mg, right? Weight's always mg, every time, on the surface of the earth. What else? What do we call that? Normal force, pushing up. The ground is pushing it up also. And so that's it, isn't it? Right? Yes.
Doesn't normal force and G
Yes.
They are going to. And how do you know they're going to?
Because it's not moving around.
Yeah, because it's not accelerating up or down. It's moving horizontal, right? So, but they are there, and it turns out they're actually important because if you look at your equation sheet, what is the equation for frictional force? Normal force times the coefficient, right? So we know that a frictional force is always equal to the coefficient times the normal force, right? The strength of the interaction with the ground, okay? And so what about the first one? It's starting from rest, and so let's think about static friction, right? When I'm pulling on something, if I'm pushing against something and it's not moving, what kind of friction is acting? Static, right? If it's not sliding, then it's static friction. Well, the equation for static friction is, look on your sheet, it's actually static frictional force it's going to vary, because if I push a little bit, the static frictional force pushes back with just a little bit of force. It doesn't, right? If it pushed back with the full strength of the static frictional force, if I pushed it this way a little bit, it would accelerate towards me. Doesn't make sense, right? It just offsets my push up until I hit the threshold, and then when I push hard enough, the static frictional force can't resist that and it starts to accelerate, right? So it's actually going to provide an infinite number of strengths greater than zero, but it's going to max out at mu sub s times normal force, right? So for me to break this thing loose, I've got to provide at least that much force against the static frictional force, don't I? That's the most that it can resist me with. Agreed? Okay, so then when I set up for part one, that's static, right? So let's set up our equations of motion, right? Because we've got this broken up into horizontal and vertical parts. So what about vertically? So if we look at the net force, I'm going to put a sub y there to tell us that it's vertical, right? What is going to be the net force vertically? It has to be zero because there's no acceleration vertically, right? So I know that whatever forces I add up here, they're going to equal zero, right? Well, what are they? What's the positive one? Vertically. Normal force is pointing in the positive direction, and mg is pointing in the negative direction, but those must equal 0. There is no vertical acceleration, right? So there's equation 1. That's important though. It's going to be a big deal to us. What about equation 2? Let's, in either order, it doesn't really matter. Let's look horizontally. Okay, so horizontally, what are the forces acting? What's acting in the positive direction? Tension. Okay, so T minus static frictional force, right? Which is going to be this, right? Everybody agree? So minus mu sub s times normal force must equal what? Well, if I'm just trying to break this free, what would the acceleration be? I mean, it would be, it's the threshold, which is what? I mean, it's, I know you want to say, well, it's got to be point, it's not, it's just 0, right? At the threshold, it's just going to start moving. I'm just going to allow it to start to accelerate, right? Does that make sense? But once it starts moving, look what happens. Then the coefficient shifts from this big static coefficient down to a much smaller kinetic coefficient. It gets easier to slide once I break it free. Like, have you ever watched sled dogs? Like, we've always had sled dogs, and I've actually run on some sled dog teams. And when they want to break the thing loose, it's just their instinct is they kind of throw themselves at the harness because they got to get the thing, they got to break it free. Once they break it free, then they can kind of settle down and get into pulling mode because it gets a lot easier to pull. But they're just, and they never want to let it stop because it's in their, they're instinctually to them, because they do this so much, they're bred to not want to let it stop because then they got to break it free again. They know some pretty good physics, I guess, those guys. So
They're like, what's this force?
You guys said levels.
So that's going to be 0, right? That's the threshold for breaking it free. Now, what are we trying to find here? We're trying to find a force, the threshold force. So a force of more than whatever we're going to calculate T to be here. Does that make sense? Okay. So we're just going to solve for T, right? In equation 2. So what do we get? We get T equals, if I add this to the other side, mu sub s times normal force. Well, we're given mu sub s right there, right? What about normal force, though? They don't give us that. But look at our first equation up here. Yeah, look at it from equation number 1. We can see right here that normal force, if I isolate normal force in equation number 1, it's just equal to mg, isn't it? Right? And so what we're able to do then is just plug in mg for normal force. Right? That's a substitution we can make. If we know that that's true, then we just get mu sub s mg, and that's our answer. Okay? You kind of start to notice some things here too, don't you? Really, all this frictional force is doing is it's just, this coefficient is telling you essentially what fraction of this object's weight do I have to pull it with to break it free, right? So if the coefficient of friction, you kind of see that? If the coefficient of friction is 0.335, it just means that I'm going to have to pull to get this thing to break it free. What this tells us, what this physics tells us, is I have to pull with 33.5% of the object's weight before I can break it free, right? And so that's going to vary. If it weighs 100 pounds, then that means I'm going to have to pull with 33.5 pounds. If it weighs 200 pounds, I got to pull with, what is that, 67 pounds, right? See how that works? But for the sake of this problem, we just plug in those numbers and get our answer, right? What's going to happen, we don't have to do the rest of this, but what's going to be, okay, that's all we need. What's going to be the force required to keep the sled moving at a constant velocity of, it doesn't matter, does it? That's just extraneous information. It doesn't matter what the constant velocity is. Acceleration would be 0, and all I'd have to do is just trade the static coefficient for a kinetic coefficient, right? Everything would be the same, wouldn't it? And then finally, down at the bottom, the last one says, what would the force have to be if the acceleration was 2? Well, then that would mean that in this equation number 2 here, we'd actually have ma, where a would be that, right? And then I would solve for t. See how that works? That's kind of, isn't that impressive that you can do stuff like that with relatively, not horribly complicated physics? All right.